Hey, fourth graders, it's another week, and I posted some more IXL things to work on. I wanted to go through and give you guys a review on any of the concepts that you thought or that you want some extra help on. So I'm going to go through all the different IXL parts that we posted for this week, and I'll give you kind of a summary and an explanation of those. If this video doesn't go far enough, please let me know and I can try to help you guys out too. So please reach out to me if you need more help. But I'm going to try to go through the ones that we already had and kind of teach about or talk about how I teach that in class, and maybe refresh your memories on how to complete these. So without further ado, let's take a look at what we're doing this week. So here's what we're asking for IXL this week. I've got the date up here. So we'll look at lattice multiplication. I'll do a review of those, and I'll do this video in this order, alphabetical order. So if you just want to look at the last one because you wanted extra help with it, then take a look at the last one, right? You don't have to do all of them. You can kind of skip ahead to that part. So kind of jump around the video as you need to. You don't have to watch the whole thing front to back unless you want help with all of these. But I'll kind of go in order. We'll talk about lattice multiplication, division, using data and graphs. We'll talk about fractions, ordering numerators and denominators, numbers with like numerators and denominators, and we'll talk about acute, obtuse, and right triangles. So take a look at these. Here's your letters and your numbers for those 5 things, and I'll kind of walk you through those. So let's take a look at lattice multiplication. I've got 3 problems here: 24 times 3, 5 times 37, and 28 times 64. To kind of start things off, I'm going to kind of go at the beginning of multiplication. We talk about multiplying 2 digits. The first method we actually show, and we show a lot of different methods, and any of them are fine, but usually the first one I always show is actually the area method. And so if I have a big rectangle, and let's say that I wanted to find the area of this rectangle, and I told you that it is going to be 24 feet long by 3 feet wide, and I know it's not to scale, so kind of bear with me here. To find the area of this, we're going to go length times width, or width times length. That's going to give me the area. So that means I got to go 24 times 3, which you'll notice is the first problem I'm doing, 24 times 3. Now, I don't know what the area of this whole thing is. It's really big. And so when we talk about area multiplication, I'm going to start just sectioning this off. And if I said, all right, I don't know how big the whole area is, but I know if this side is 20 and this is 4, this line here is 20 and this one is 4, together it'd make a length of 24. I do know what 20 times 3 is. So if I want to find the area of 20 times 3, right, I can do that. And so I'd be talking about the area then of this red box right here. The area of this red box would be 20 times 3, which is equivalent to 2 times 3 is 6, add a 0, 60. So the area of the red box is 60. The area of this blue box then is going to be 3 times 4. And 3 times 4, when I do that, 3 times 4 is going to be 12. So if I know that the area of the red box is 60, the blue box is 12, then I can figure out the area of the green box. I'm just going to go 60 plus 12, and I would get that. So 60 plus 12 equals 72. And so the area of this box, or 24 times 3, the area of the box, would be 72. Hopefully that makes some sense to you. That's the area method again. Now I'm going to hold on to this idea here. And so I'm just going to save this and tuck it away for a second. Okay, and I'm just going to move this over here real quick. We'll come back to it. I'm going to delete the rest of this though for now. And we'll talk about the actual lattice side of it. So if I want to do 24 times 3, these are the lattice boxes you're usually familiar with. I'm going to make a 2 by 1 box. And I'm going to go my diagonals, diagonals. And I'm going to do 24 times 3. So I set this up here and here. I'm going to multiply for each box. I'll put in some lines here. We got to go straight down and over and straight down and over. So for this first box that I want to fill in, it's going to be 2 times 3. What is 2 times 3? It's 6. And I can't just put a 6 in here because I've got 2 sections. So when I write in my 6, I'm going to write it in as 0, 6. Great. Now I've got 4 times 3. When I do 4 times 3, I get 12. And I will write in 12. 1, 2. And so now you can see 2 times 3 is 6. 4 times 3 is 12. And I've got these 2 numbers here. And now I'm just going to add on the diagonals here. And let's see if we get the right answer. Remember, I don't add anything outside of the box. So when I'm adding on the diagonals, this first number is just 2. I'm just adding on the diagonal. So it's just going to be a 2. Again, I'm just adding right here. 6 plus 1 is 7. And 0 plus nothing is 0. And I could write a 0 in, or I could just leave it. But my answer I got here is 72. You can see it there, 72, just like the answer in the last one. Now I do want to show you something with this and where all these numbers kind of come from and compare it to the area method. So let me just tuck this over here for a second so we can compare the two. Let me get rid of all of this stuff here. So let's look at these. Here's my lattice problem. Here's my area method problem. I did these separately. But let's compare them. If you'll notice, I did 60 plus 12 here. So 60 plus 12 to get 72. 0 plus 2 is 2. 6 plus 1 is 7. That's how I got 72. You'll notice I actually did the same exact thing here. Right? I've got 2 plus nothing. 2 plus 0. 1 plus 6. 1 plus 6. I get the same numbers. By doing this diagonal, I get to add up the numbers in the tens column. And if there would have been hundreds column, it would have came over here. So we get the exact same numbers. It's just a different way of doing it. So 24 times 3. Here's my ones. Here's my tens. And if I would have had 100, it would have been over here or here. But it's 0. So you kind of compare those. So let's just do another problem, and I'll just focus on the lattice part. So let's do 5 times 37. Now, if I do 5 times 37, that is the exact same problem as 37 times 5. You can flip those around in multiplication or addition. It doesn't matter the order. And I like to flip them around. I think it makes things easier because then I can use the same box. Put in my diagonals. And now I can do 37 times 5 and multiply this out. It does not matter where you start, whether I go 3 times 5 first or 7 times 5 first. It doesn't matter. I like to start over here. So let's start with 3 times 5, which is 15. Now I do 7 times 5, which is 35. And I've got my boxes filled in. I add on the diagonals. 5 plus nothing is 5. 3 plus 5 is 8. 1 plus nothing is 1. I get 185. Okay, let's try one more together. And you can try to do it on your own and check your answers, but I'll do this one. Now it's a 2 by 2 number, so my box is going to look a little bit different. Now I'm going to make a big square, and I'm going to turn it into smaller squares. Kind of looks like a window pane. And then I'm going to put in my diagonals, corner to corner, corner to corner, corner to corner. 28, 64. And if I would have wrote out 64 times 28, I'd get the same answer. It really doesn't matter the order. And again, it doesn't matter which order I multiply in. I like to start up in the corner, but I'll do 2 times 6. Then I'll do 8 times 6. Then I'll do 8 times 4. And I'll end with 2 times 4. So as long as you're going straight up and down and across, you'll end up with the right things. So the first one I said that I'd do was that red one. Let's do 2 times 6, which is 12. Now I'm going to do 8 times 6. 6 and 8 went out to escape, made the figure 48. I'm going to do 8 times 4. For 4 trick is just double it and double it again. So 8 plus 8 is 16. 16 plus 16 is 32. 2 times 4 is 8. I can't just write an 8. I have to put a 0 in, so I've got a placeholder. So it's 0, 8. Now I add on my diagonals. Let me switch colors. Always, you do have to start on the right side. So I'm going to start with 2. 2 plus nothing is 2. 8 plus 3 is 11. Plus 8 more is 19. So I'm going to put my 9, carry the 1. I always put it right up here. You got to carry the 1. So I end up with 19. I put my 1 up here, so I've got to add 1 plus 4 plus 2 plus 0. 1 plus 4 is 5, plus 2 more is 6. So now I put my 6 here, and 1 plus nothing is 1. My answer then is going to be 1,692. Hopefully that helps with your lattice multiplication. With division, I actually did a really long video, and I'll post it in I'll post the link to it as well. So I'm going to do this one pretty quick. But you'll be doing a 2-digit divided by a 1-digit. So my 2 examples are going to be 72 divided by 5 and 94 divided by 3. So when we write these out, 72 goes in the middle. I do what I always call those hangman gallows. If you're playing hangman, you kind of draw a shape like that, and a 5. So when we do this, I'm going to ask myself, all right, how many times? 5 times what gets me close to 72? 72 is my target number right now. 5 times what gets me close to 72 without going over. And try to pick easy numbers to work with. So I would usually start with a 10 here. I think that would make the most sense. And so if I had 72 things, and I gave 5 different people 10 things, how many did I give away? I've got 72 things divided between 5 people, so if I give them each 10, that would have been 50 total things. Right? So 5 times 10 is 50. If I gave out those 50, I subtract it. And 2 minus 0 is 2. 7 minus 5 is 2. And I've got 22. This is now my new target number, 22. 5 times what gets me close to 22 without going over. Probably a good one for this would be something like 4. 5 times 4 would give me 20. I subtract, and I get 2. I can't go any further. If I were to put a 1 here, I would have to go 2 minus 5, and I can't do that. That's not possible. So I'm done. This is as far as I can go. So now we just have to add these up. 10 plus 4 is 14. All right? And my remainder, I've got 2 left over. So I got 14. My remainder is 2. Some people like to write that as 14 and 2/5. That is also correct. So either one is the correct answer, but that's what we end up with. Just going back real quick on this one, if I wanted to, if I go back a few steps to where I was here, the nice thing about this is you don't have to be right all the time. Maybe I didn't know 4 times 5 gets me 20, and that's pretty close, so maybe I did instead like 3. And so I put in a 3 here. 5 times 3 is 15. As long as my numbers are smaller, it's fine. I can subtract 2 minus 5, can't do that. Comes a 1. Now it's 12 minus 5, 7. I got 7 left over. And now I could do 1. And I end up with the same answer. It's just an extra step. Because now if I were to add these together, 10 plus 3 plus 1 is still 14 with my remainder of 2. So there's different ways to get the same answer. So that's the nice thing about this method. Let's try one more. This time we're going to do 94 divided by 3. You can try this at home, and then I'll go over it, so you can just pause the video while that happens. I set it up this way with my hangman gallows. 3 times what gets me close to 94 without going over, just like the Price is Right. I want to get close to it without going over. 94 is my target number. If you look at just the first one, I see a 9. Well, I know 3 times 3 would give me 9. So if I wanted to, I could put a 3 here, and that would give me 9, except I don't want 9. I want 90. Well, 3 times 30 would give me 90. And I get really close already. The closer you can get with these, the faster it ends. So 3 times 30 would give me 90, because I know 3 times 3 is 9. So 3 times 30 would give me 90. And I can subtract these. It makes a nice, easy subtraction problem. I just get 4. I could add a 0 here or just leave it. 3 times what gets me close to 4 without going over? A 1. And I get that left over. So my answer, 30 plus 1 is 31 with a remainder of 1. Or I could have written it as 31 and 1/3. Both are correct. So sometimes you'll have remainder, sometimes you won't, but hopefully that refreshes your memory. Again, I've got a much longer video on this if you want more help. Talking about data and graphs, we're going to read a table, and we're not talking about this kind of table, right? We're talking about data. And for this one, I actually pulled out some sample questions from IXL. So let's take a look at them. Here's one of the first ones. You might even see this one because I did pull it right off of IXL. So this one says, a county agency recorded the money donated to several charitable causes over time. So it's listing these different charitable causes: animals, parks, hunger, education, medical research. And it's got the months of April and May here. So it's a bunch of data. It's just information. Each one of these numbers is a piece of data. Use the word data to describe those. And this chart is just trying to organize all of this information. Instead of saying animals, $3 in April, parks, $19 in May, hunger, I mean, this could all be written out in a long way or put in a chart so it's easier to read and understand the numbers. So the question is, which cause raised more money in April, hunger or medical research? So now we have to cipher this out and figure out what information is important. So we're only talking about the month of April. So I'll start by just looking at the month of April. And I'm just going to highlight the month of April. It's only these numbers that I'm worried about. I don't really care about May right now. I just want April. So which cause raised more money, hunger or medical research? So now I'm going to look for hunger and medical research. I'm just going to highlight those two. Here's hunger and here's medical research. So now where these overlap are the two numbers that I'm most concerned about. I'm really only worried about this number and this number. So which raised more money in April? April, is it hunger or medical research? Well, 14 is more than 1. So my answer to this one would be medical research. So when you do this, just make sure you're looking up and down. There's a lot of numbers, like everything else in here doesn't matter to the problem. They were only looking for these two, so I had to find them. So it's just finding that information and understand what's important. If you use the tool down here on IXL, there is a highlighter tool, so you can kind of highlight the information that is most important. Let's try another one. Okay, so this one says, while looking through an almanac at a library, Rob noticed some data showing the population density of various states. That's how many people live like in a per square mile area. So even though a state might be really big, there might not be very many people in it, so they've got a low population density or something like that. So bigger cities have higher population density. They're talking about how many people live in a typical, on average, in a square mile. So the state, here's our 3 states. They got Wyoming, South Dakota, and Nevada. And then they've got the years 1990 and 2000, so 10 years apart. And the population per square mile. In 1990, which of these states shown had the fewest people per square mile? So again, we just have to cipher out this information. We're only looking at 1990. So I'm going to highlight 1990 because that's the only set of numbers I really care about right now. And then it's asking which has the fewest, which means smallest. So which is the smallest number in that column? And if I look at the numbers of 4, 9, and 10, 4 is the smallest number. So the answer to this would be Wyoming. Because if 4 is the smallest number, which it is, then Wyoming is the state. State, year. So Wyoming would be my answer. Because fewest means smallest. Okay, let's try one more. Pull this up. Last one of my examples. This one says, an auto manufacturer, so people who make cars, track the number of vehicles sold by each of its dealerships. Here I actually use the highlighter tool that IXL has. And it's asking how many more cars than SUVs did Swanson's Auto Mall sell. So in this case, I'm only concerned about Swenson's Auto Mall. I don't care about the other ones. These numbers are really not important to the problem. It's not important, so I can kind of cross those off. So how many more cars than SUVs did it sell? When it talks about how many more than, we're actually going to subtract, right? Because if person A has 1 pencil, person B has 2 pencils, how many more pencils do they have? I wouldn't add those 2 numbers. I wouldn't say it's 3 pencils. You actually subtract them. So in this case, we're going to subtract them. So it would be my 2 numbers are 17 and 10. And if I subtract that, I get the answer of 7. So 7 would be the answer. They sold 7 more cars than SUVs. So the main thing with this is just figuring out what information is important and knowing what to do with that information. It might ask you to combine them. It might ask you to find the difference, such as this one did. But you have to figure out what information is important. And now on to fraction, equivalence, and ordering. So we're talking about numbers with like numerators and denominators. So first off, a numerator is the number that's on top of a fraction. The bottom one is the denominator. Denominator. I always remember that because D down. That's how I always remember that. So your N is on top, your D is on the bottom. D for down. So if I wrote a fraction like 1/2, a very common fraction you might see anywhere, the 1 is the numerator, the 2 is the denominator, right? It's always the part over the whole. And so in this case, 1/2, 1 is the numerator, the 2 is the denominator. So hopefully that part helps. Now let's take a look at doing some fractions. So we're going to order some with like numerators and or denominators. So that's going to give you a bunch of fractions with either all the same numerators or all the same denominators. So let's start with thinking about some pizzas. Let's say I have a pizza here. And actually, let's say I have multiple of them. Let's say I have 4 pizzas. They're all the same exact size. Okay? But let's split these pizzas up. And let's say this one I'm going to cut in half. This one I'm going to cut into thirds. This one I'm going to cut into, let's say, fifths. I want to make like a person, stick figure, stick arms, and stick head. All right, there we go. And this one, maybe I'll make it tenths. Let's try to do tenths here. If I can do tenths. There's my tenths. Okay? So, if I said you can have one slice of pizza, and you walk in and there's 4 different pizzas out of it. You have 4 pizzas. I said you can have one of these slices. I don't care which one, you can take one slice. If you were really hungry, would you want to take a slice from here, a slice from here, a slice from here, or a slice from here? Keep in mind, when we write these as fractions, this would have been 1/2, 1 out of 3, 1 out of 5, and 1 out of 10, right? So those are my different fractions. They all have the same numerator, common numerators. The top number is the same. So which one is the biggest out of these? Well, actually, even though 2 is the smallest number, this is the biggest fraction because 1/2 is a lot more than 1/10. So it's already in order from biggest to smallest. And people get thrown off because 10 is a big number, but it's actually, when you're talking about 1/10 of a pizza, it's a very small amount of that pizza, right? If I threw another one in here and I had a pizza that was sliced into 100 slices, 1/100th would be a tiny, tiny amount, where 1/2 of the pizza is a huge slice. So actually, when we talk about numbering these with common numerators, the smaller the denominator, the bigger the slice, because I'm dealing with 1 out of only 2 versus 1 out of 10. So kind of think about these when you're ordering them, of how it makes sense. So again, these are like numerators. So let's try another one with like denominators. So now I've got 4 pizzas again, and I've divided them all into eighths. So every one of these pizzas is divided into eighths. And this one might be a little bit easier. So now I've got common denominators. All the bottom numbers are the same. All right? And if I wanted to figure out which one, if I wanted to put these in order, let's say this one has this many shaded in. This one's got this many shaded in. This one's got this much shaded in. And this one's got this many shaded in. What are these fractions? Let's count them out. So here I have 8 pieces, and 1, 2, 3 are shaded in. So that would be 3/8. This one's got 1, 2, 3, 4 of them shaded in. So that's 4/8. Many of you might recognize that as 1/2. Here I've only got 1 shaded in. Here I've got all of them but 2, so it's 6/8. Which one is the biggest amount? If I want to order them, maybe I have to do this one from smallest to biggest. Let's rewrite them so that they're smallest to biggest. Which one of these is the smallest amount? 1/8 is the smallest. So now The smallest amount is just the smaller numerator. This one's a little bit easier. The biggest amount would be 6/8, and in between there, you would have 3/8 and 4/8. So now my numerators are actually going up in order. 1, 3, 4, 6. Because 1/8 would be the smallest amount, 6/8 would be the biggest amount. If I said you could have pizza and you were really hungry, would you want 1/8 or 6/8? 6/8 is the most, that's the biggest. So it's a little bit different when we have common denominators versus common numerators. They actually go in opposite order. Okay. Last one. We're talking about angles, specifically triangles, but I want to review angles first. So right here, I've got this angle. We're always talking about, or in this case, I'm talking about the interior angle. So I'm talking about this one, this angle, and this angle. If I'm starting up here, this is a small angle. It's smaller than a right angle. It's little. It's cute. It's acute. So we call this one an acute angle. Most of you guys know that. So here's my acute angle. Right there. It's little. It's cute. This one is really big. It's a big angle. So we call it obtuse. We say that obtuse because it's a big angle. So there's my obtuse. And the last one is right. I can test it using something really scientific like any square little post-it or something. If I put this square in here, you'll notice that it fits perfectly in here. This square, this corner has these square angles, so we call that a right angle. There are no left angles, there are no wrong angles, but there are right angles. And so this one is a right angle right here. So knowing that, it's important to know the difference between acute, right, and obtuse, so that when we start talking about different types of triangles, we can figure out what they are, because I could turn any one of these shapes into a triangle. I can turn these three different angles into triangles by just connecting the dots, connecting corner to corner, or the ends here. And now I've got three different triangles. And actually these keep the same names. If you look at this one, I've got 1, 2, 3 different acute corners. This is close to a 90, but it's actually less than a 90-degree angle. I can test it by moving this over and spinning it. You'd be able to see that it is actually less than a 90-degree angle. And since this shape has nothing but acute angles, it is an acute triangle. So an acute triangle is any triangle that has all acute, spell acute right, acute sides, angles. Okay, so an acute triangle has 3 acute angles in it. Every single angle is less than 90 degrees. In a right triangle, which is this one, there's 1 right angle. It's always going to have 2 acute angles, but it's got 1 right angle and 2 acute. And with an obtuse triangle, there's 1 obtuse angle and 2 acute angles. So all triangles are going to have at least two acute angles. Every triangle will always have 2 acute angles in it. You can't draw a triangle and have an obtuse and a right angle in it or anything like that. It's not possible. You can try it, but you can't draw a triangle with an obtuse and a right angle in it. You're always going to have 2 acute, and it's whatever the other one is. If it's got a right angle anywhere in the triangle, it's a right triangle. If there's an obtuse angle anywhere in the triangle, it's an obtuse triangle. And if it's got all acute angles, every single one of them is acute, then it's an acute triangle. So it's pretty straightforward just by looking at it that way. Again, if you're not sure, get a piece of square, anything, a Post-it note works great, and you can just kind of tuck it in the corners and see if it's bigger or smaller, if those angles are bigger or smaller than that Post-it note. If it's smaller, it's acute. If it's bigger, it's obtuse. If it's exactly the corner of a square, then it's right. So just kind of pay attention to those and I think it's fairly straightforward. I hope that review really helped you guys. If you have any questions at all, please let me know. I'm happy to answer any more of your questions. But hopefully this video put together makes a little bit more sense. Remember, there is a longer division one as well. But otherwise, if you have any questions, please let me know. Hope you guys have a great week. Talk to you later.